lectures, you need to go to My Math Lab on the left. You should look for Multimedia Library. Choose the chapter and the section. In this one, it's going to be Chapter 1, Section 1.1. And check PowerPoint and review all the terminology, and then there's a few examples. But you really want to do the terminology or write down formulas that you may need before we get started. Because once we get to this point, this is me just talking you through a few examples and showing you some work and some extra practice. So we're going to start first with, you read the definitions for inductive and deductive reasoning, and these are also examples from the back of the textbook, which are included in your e-text if you need to see those, but usually I have enough information that you can just follow along with me. But this first section, number 1, is just determine whether the reasoning is an example of deductive or inductive reasoning. So I'm going to read a statement, and we're going to think about it, and then you're going to determine what it is. So the first one is, if a mechanic says it will take 7 days to repair your car, then it will actually take 10 days. The mechanic says, I figure it'll take a week to fix it, ma'am. Then you can expect it to be ready 10 days from now. So in this case, it's going to be deductive reasoning because you were given a general principle and then applied it to a specific case. So here we're going to say deductive. All right. The next one is, it rained every day for the past 6 days, and now it is raining today as well. So it will rain tomorrow. That's inductive reasoning because you're given you are drawing a general conclusion after getting repeated observations. So we see that it rains, it rains, it rains. Then we can say, well, we think it's going to rain. So this is inductive. All right, the next one. If you build it, they will come. You build it, therefore they will come. So this is deductive. If you have some type of rule, then you follow through. So if you build it, they will come, and then that's what goes on. This is a deductive statement. And then the next one is, it is a fact that every student who ever attended Delgado University was accepted into graduate school. Because I'm attending Delgado, I can expect to be accepted into graduate school too. So this one is an inductive case because they're saying every student who ever attended Delgado. So we see a student, we see a student, we see a student, we see a student. So we could see by multiple examples, then we can apply that if you attended Delgado, that you'll be accepted into graduate school as well. So this one's inductive. And inductive deductive can seem a little tricky at first, but once you get in My Math Lab and you start working through the examples, I think you'll feel a lot better about that. Sometimes just reading them verbally and hearing them, it might seem a little confusing to you, but I think you'll be okay once you get to some of your own homework examples. Alright, so this next section, we're just basically going to look at a pattern and establish the next term. And some of these you're really good at, and some of them are intuitive. And other examples I picked particularly so that you can see the types of patterns that they use to make the next term. So we'll start with some of the basic ones. And one of the ways to do this with the video is you can pause me, look at it, and then check to see if you got my answer. You know, give yourself as much time as you need. I'm pretty much going to roll through these, but slow me down. Test yourself, and then check your answer. Alright, so 6, 9, 12, 15. This one's a pretty easy case. You can see that it looks like we're going up 3 each time, plus 3, plus 3, plus 3. 18 plus 3 is 21 is going to be the next term. Very basic. Okay, another common thing is to have multiples, or multiply or divide by a particular number. So in this case, you can see we're multiplying by 4. 3 times 4 is 12. 12 times 4 is 48. So we're going to continue that pattern and do 768 times 4, which is just going to be 3,072. Okay. Number 18, we want to look at it like multiples. It's going down by half. So that's either multiplying by half, or you can look at it like dividing by 2, whichever you're more comfortable with. So when we get down here to the end, 2 divided by 2 is just going to be 1. So that one is multiplying by 1/2, or you're dividing by 2. Alright, 19. 3, 6, 9, that looks like plus 3, plus 3, plus 3, but then we get to 15, so that's different. So then I'm going to start back over and look at it again. One of the common things they do is 3 plus 6 is 9. So sum of the previous two. So then to get 6 plus 9 gives us 15. 9 plus 15 gives us 24. 15 plus 24 gives us 39, and then 24 plus 39 gives us 63. And so what you want to call this one is sum of previous two. That's a common pattern, so add that to your list of tools when you're looking for patterns. Okay. A fraction. Multiplying fractions by multiples isn't too bad, but we can see that that's not happening here because it's 1/2, 3/4, 5/6, 7/8, 9/10. And when you add fractions, you have to have a common denominator, so that gets to be real messy, and none of those denominators are the same, so we don't think that's what's going on. So the next thing is look in the numerator. 1 plus 3 plus 5 plus 7 plus 9, that's odd numbers. The next one would be 11. In the denominator, 2 plus 4 plus 6 plus 8 plus 10. The next one is 12. So we identify the pattern in the numerator versus the denominator. Okay? Alright, moving on. 22. 1, 4, 9, 16, and 25. So we look for multiples. It's not going on. Addition, so plus 3, plus 5. So another thing you can look for is squares. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared. So the next one would be 6 squared, which is 36. So squares, you want to add that one. Now 25, multiples don't work. Multiplying by a particular number each time is not happening. Adding by a number each time, let's see what happens here. So I have to say 4 plus 3 is 7. 7 plus 5 is 12. 12 plus 7. 19 plus 9. 28 plus 11. It looks like they're adding odd multiples. So 3, 5, 7, 9, 11. So the next one would be plus 13. So I need to do 39 plus 13, which is 52. Yeah. So that's also something you can look for. If you can't establish any of the intuitive ones, then try to start looking for patterns like that. Alright, this next section is by far your favorite because you all do really well with these and it's pretty easy to identify. We're going to look at this step, compare it to this step, and then compare it, and then you're going to give the next step. So we can see the only difference is we added an 8, we went down 1 here, and we added an extra 8 in comparison to the first statement. Alright, when comparing the next one, we added a 7 to the previous one. We went down 1, and we added an additional 8. So we're going to continue this pattern. So when we choose the next one, we're going to do 9, 8, 7. We're going to add a 6 here. Leave that alone. Instead of 5, we're going to go down 1. Then we're going to add an extra 8. So we'll have this here. So establish the pattern and then continue the pattern. Alright, we're going to look at number 33. We can see that this left number did not change. That's easy. 3, 6, 9, 12, 15 would be the next number. When we're comparing over here, 1, 2, 3, 4, 5. All zeros next. 1, 2, 3, 4, 5. All zeros next. 1, 2, 3, 4, 5. Okay? So like I said, those are your favorites. You usually do really well with those. Okay, these next two, we're going to use method of Gauss. And this is a mathematician called Frederick Gauss. He established this, and so what they want you to do is add all the terms between 1 and 200. So these dots mean every term in between those. We just don't have them written out. So 3 plus 4 plus 5 plus 6 plus 7 all the way up to 200. Now, I'm going to show you how to use this method because we're not going to take all that time to add all those up in between. What you want to do is you're going to take the first term and the last term. So if I take 1 and 200 and I add those together, that pair is equal to 201. Then if I take 2 and that second to last term there, in that case, which is 199, and I add that pair, it's going to be 201. If I take my third term and my third to last, which would be 198, you can see that equals 201. So each of the pairings, it's pretty obvious they're going to equal to 201. Now, how many terms total? 200. Well, if we pair, take the 200 and put them in pairs, that's 100 pairs, right? So if we have 100 pairs, and each of the pairs all equal 201, we can multiply that out, and 201 times 100 is 20,100. That's going to be the sum of all those terms. Okay, so we're going to do this one. Try this next one, pause it, try this next one on your own. Okay, so we'll take 1 plus the last term. Get 801. We'll take 2 plus the second to last term, which would be 799. Then we take 3 plus the last term, third to last term, which would be 798, sorry. And that's equal to 801. Alright, so we know each of the pairings is equal to 801, but then we have 800 terms altogether. If we pair them in twos, there's 400 pairs. Well, 400 pairs all equal 801. We can find out what that sum is going to be, and that's going to be 320,400.